Hello guys, this is Udaya Kumar, final year Biomedical Engineering from SRM University. I am here to present my final year project work. We are working on the project Non-Invasive Assessment of Fractional Flow Reserve using computational fluid dynamics obtained from Coronary CT Angiography images. Fractional flow reserve. Fractional flow reserve is a measure used to determine the extent of narrowing of a coronary artery stenosis. It is a guide wire based procedure used to determine blood flow and pressure across a specific part of the coronary artery. FFR is usually measured as a ratio of pressure behind to the stenosis relative to pressure before the stenosis. Here is a short animation to demonstrate the invasive FFR procedure.
Fractional flow reserve, or FFR, is defined as the fraction of maximum achievable blood flow that can still be maintained to the myocardium despite the presence of a stenosis. During maximum hyperemia, FFR can, through a series of simplifications, be calculated as distal pressure, PD, divided by proximal pressure, PA. Let's look at an example. PA is measured via the cath lab's standard AO transducer, here 100 mm mercury. PD is measured by the pressure wire sensor, located distal to the narrowing, here 70 mm mercury. 70 divided by 100 gives an FFR of 0.70, which means that only 70% of the maximum achievable blood flow is reaching the myocardium.
FFR has a theoretical value of 1. Those stenosis that have value less than 0.75 corresponds to inducible ischemia and will require interventional treatment to treat that stenosis. But for those stenosis whose value is greater than 0.75 can be treated with medicational treatment and without the need of angioplasty. Since this procedure is an invasive procedure, it can lead to many complications such as coronary artery dissection, embolism, coronary artery spasm, acute renal failure, myocardial infarction, stroke, and may also lead to death. In order to avoid these complications, we have used a technique to determine fractional flow reserve non-invasively. We have proposed that recent advancements in coronary imaging and computational fluid dynamics can serve as an alternative to this invasive FFR procedure. We obtained coronary angiography CT images and we generated a 3D model of the coronary artery from it. And then computational fluid dynamic analysis is done on that part of the coronary artery to determine the blood pressure across the stenosis. We used Mimic software and Thematic SQL software for 3D modeling of the coronary artery and ANSYS Fluent for performing the computational fluid dynamic analysis. Now let us discuss about the detailed methodology used in our project.
Segmentation of coronary artery is done using Mimics. Initially, the images are imported into Mimics, and the orientation is set. This block corresponds to the coronal view. This is the sagittal view. And this corresponds to the axial view. This is the block in which the 3D components are shown. The first step in segmentation is the thresholding. Thresholding is nothing but setting a maximum and minimum value of pixels. All the pixels in the image, which lies in between these range, will be highlighted. Then region growing operation is performed. When clicking on the object at the point of interest, all the points that are connected to the clicked point will be added to the target mask. Now let us calculate the 3D for this mask. You have to delete all these unwanted regions from the mask, which can be done by edit mask. You can erase the unwanted portion in individual slice, and then the 3D object is created. This is the complete 3D segmented model of a coronary artery tree. Now this is identified as the region of interest, which corresponds to less than 30% stenosis in left anterior descending coronary artery. After performing cut and split operations, we obtain this model. This 3D model can now be exported as STL file. The STL file exported from Mimics is imported into 3-matic STL software. This is the software used for the post-processing of the 3D model. Once the topology-optimized data is imported, various operations such as smooth, reduce, subdivide, trim are performed, and the output model is obtained as this. Now the morphological measurements are done in order to identify the stenosis percentage. This is the complete post-processed 3D model of coronary artery. This model is now exported into .step files so that it can be imported into ANSYS Workbench. Fluid flow fluent is used in ANSYS Workbench. The .step file obtained from 3-matic STL software is imported into the Design Modeler panel. After importing, the geometry is generated. Then Meshing module is opened, the geometry is loaded. Then, named selections, such as inlet, outlet, and wall are defined. Now the body sizing and inflation are set and the geometry is meshed. ANSYS uses unstructured meshing in order to reduce the amount of time you spend generating meshes. After meshing, the Fluent launcher is opened. Double precision is chosen. Pressure-based type of solver is chosen. And steady-state time analysis is set. Blood material with constant density and velocity is created. Boundary conditions for inlet, outlet, and wall are defined. Inlet will be assigned with the constant inlet velocity value. Outlet will be assigned with the constant outlet pressure value. Wall will be assigned with no slip conditions. Then solution methods are set. Simplex scheme is chosen. It aids in convergence speedup. Convergence monitors are set up. The solution is initialized. The default initialization method, for single-phase steady-state analysis, is hybrid initialization. Calculation is run with 100 iterations to reach a converged solution. Convergence is plotted. Residual scales are plotted. Contour plot of total pressure is plotted from which the FFR values are computed. The pressure measured proximal and distal to the stenosis are tabulated in this table, along with the FFR value. The first stenosis has 0.93, second, 0.81, third, 0.75, followed by 0.62 and 0.58. Out of 5 coronary lesions, 2 has been detected as the hemodynamically significant lesions, and they correspond to inducible ischemia. They will require interventional treatment to restore normal coronary blood flow in that region. The remaining 3 lesions are less significant and can be treated with medications without angioplasty. For vessels with stenosis percentage less than 30% detected by CCTA, the value of FFR is assumed by default as 0.90. For stenosis with greater than 90%, it is assigned as 0.50. Some of the limitations for our project includes the diagnostic accuracy of FFR, computed from CCTA, is influenced by a number of potential limitations, which includes CT imaging artifacts, such as misalignment, patient movement, image noise, breathing of patient, etc. CCTA image does not provide sufficient quality for the accurate segmentation of the 3D model, because of tachycardia, arrhythmia, calcification, etc. The usage of adenosine may overestimate the degree of vasodilation. Choosing boundary conditions in some cases appears challenging. CFD simulation is computationally time-consuming technique. In the present study, the non-invasive assessment of computing FFR from CCTA using computational fluid dynamics modeling has been developed to replace the invasive procedure, which a number of risk factors. This study involves only with the coronary angiography, and no other imaging or post-imaging procedures were performed. The computation of FFR from the same patient invasively can give us the conventional FFR value, and the FFR value computed from CCTA can be compared in order to determine the diagnostic accuracy of the FFR computed from CT. If all the limitations are overcome, then this method will be a substitution for invasive FFR procedure in determining the severity of coronary lesions. These are our references.